Why the options pattern is great for security. Hello, my name is Dima Kotik. I'm an application security engineer at Security Journey. We provide training for all matters related to security that is for developers and by developers. I am obsessed with service reliability, and I'm also excited about Golang. Examples in this presentation will be in Go because I like it and they fit very nicely on the slide. There is my Twitter handle if you would like to have a conversation after this presentation. Today we have 4 goals that we would want to accomplish with our exploration of the options pattern. And those are, first, we're going to review the options pattern for complex object initialization. Second, we will discover the types of vulnerabilities that the pattern can help us prevent. Third, we will improve the classic paradigm to maximize the security, and we can do that very well. And finally, I hope this talk inspires you and other developers to adopt the pattern when it fits. There's much to be gained here. To get started, let's define the problem we're trying to solve. OWASP Top 10 for 2021, number 5, is security misconfiguration. Last year, this was number 6. So this particular problem has increased. It doesn't matter how strong your application is, how many different firewalls it has, and different analytical tools and testing tools, all the CI/CD magic. If it is misconfigured, it will be taken advantage of. And this category in OWASP testifies that this happens a lot more often than many other vulnerabilities that we are afraid of. Second, now OWASP has added a category called insecure design. I would argue that programs that can be misconfigured and are misconfigured are insecure by design, and there are some things that we can do about it to prevent that. So this is a prevalent problem, and attackers love this. You can have a situation where your program has a hamstrung cipher. It may be capable of using all the best ciphers, but it has support for some of the legacy ones, which were enabled by a faulty configuration. A short key was provided by mistake, or an insecure source of random. This happens, and to attacker, this opportunity is like a piece of candy. How often we have programs that have missing access controls, or a misconfigured access control that expected a certain user group that was left blank, and the program interpreted as no access control at all. So an attacker who belongs to no group at all just waltzes right past all the access controls and accesses an endpoint that should have been secure. This happens a lot. We also have debug backdoors left in our services. We need additional instrumentation, we need additional observability in our services, and designing them and building them into our application can help us in the development stage. It is often the situation that they are left by mistake to run in production. The service is deployed, but all those additional helpers remained. And perhaps they were not supposed to be there because they were behind a feature flag or a little environmental variable called debug equals true. And it was set to true at the time. And now an attacker found a way to do whatever they would like with their service. This is just a few examples, but you can imagine so many more. All of those go back to misconfiguration. And you can see how easy it is for the attackers to exploit those opportunities, and so they usually check for those things first, because it is the most power given to them with the least amount of effort on their part. The problem with security advice that's currently out there regarding misconfiguration is that it's not really all that helpful. We have basically 2 different categories of advice. One is we're called to stop misconfiguring services. Yes, double check everything. Don't make those types of mistakes, and I don't think that will really help us much because our services are more sophisticated than ever. There's more of them. Then there's the whole cloud layer, which is very opaque sometimes and difficult to work with. And also our teams are large and they're more remote. They span time zones and they span languages and cultures. And it's just a matter of time before somebody misunderstands, by accident loads an older version of the configuration file, or removes a commented outline by mistake that leads to misconfiguration. And simply telling people to stop doing it is like telling them to stop being human. We are human, we will make mistakes. So it's good to be reminded, but it's not really practical business strategy. The second one category is also the call to use a scanner of some sort. Policy validation, policy-based validation, or perhaps a static analysis tool, a dynamic analysis tool. We have hundreds of configuration validators these days, things that are based, for example, on open policy, agent, or QLang. You can run configuration files through validators written for policies, right? But the problem is, for you to catch misconfiguration, you need to forecast what the problem is going to be. The tool needs to know the problem ahead of time, or the person writing the policy needs to know it. And the cost of discovering a misconfiguration is tremendously expensive. You already lost your data, you already compromised your users, and now, of course, you will write that policy, but that may be too late. So this is great. We should be using scanning tools, but we need to remember that they catch mostly the most obvious and egregious misconfiguration cases, but when we have custom solutions or we combine multiple solutions, there's just no way to foresee every different way something can be misconfigured and how configurations interact across boundaries. There's just no way. So the question here really is, can we do something engineering-wise to help with this problem? And the answer is yes, we can. Enter the options pattern. So what is the options pattern? The options pattern is a flexible object provisioning strategy using a list of independent object modifiers. So let's imagine that our package or our class is an engine, and we're going to just go and take it through stages of applying different tools to it. And each tool is only designed to tweak one or two parameters to get our engine ready to run in production. Each tool is narrow in scope, and each tool is applied only once. This is the basic idea behind the options pattern. To grasp it, let's go back to a Java classic, which will help us understand how this whole thing works. And the Java classic is, of course, the builder pattern for object initialization. The options pattern works similarly on the surface, but there are some significant differences that have ramifications for strong software design and security. So in our first example, here's an example of using a classic builder pattern where we have, say we want to have a bank account builder, and it will be a class that will construct another class called bank account, and we will supply, by calling methods, different parameters to our builder, and finally we will call the build method and have our bank account. In the second example, it's the same idea, but using the options pattern. And the difference here is that instead of using a class, we will use a constructor function that will take a list of object modifiers, a list of options. And by convention, we start those with the word with, and we'll take those parameters, each one of those options, typically a closure. We'll tweak that parameter for our bank account, and there's no need to run the build method because the options initialization step, the constructor will apply the series of those modifiers and return the result. So the options pattern is kind of like a cousin of the builder pattern. It's superficially very similar, but one way to differentiate them is to think of the constructor pattern as one object preparing another. For the options pattern, the object is prepared using a list of modifiers, a list of options. Those are typically closures. Let's look at the classic. This is how I first learned functional options from the Go community, and it took me a while to appreciate the value of it. This is just a really simple example. First, we will define a type called option, and an option will be just a function that will take a pointer to the thing we're trying to construct. In our example, it's a bank account. And once we have defined the type, let's create one option. We can make as many as we want, but let's create one option and call this option with email. With email, we'll take a string and return an option. This is a closure, second order function, right? And so it will return a function wrapped or hidden inside another function. And inside the other function, we will actually take our object B, which is bank account, and we'll apply that supplied email to our parameter client email. Please note that, of course, in Golang, client email is with a lowercase letter, and that means that it is a private parameter. When we're using options pattern, object initialization, we want to protect our private parameters and not make them accessible by external modification, right? So we don't want people to go and change our values without going through proper modification channel, safe modification channel, which is our closure. So only we want to have access directly to the parameter. Otherwise, if people want to change, then they have to go through the option. And that's the main point here, right? So we keep those parameters hidden under wraps and private. Can we improve this pattern, this classical pattern, in any way? And we can. We can improve it by applying 4 classical failure conditions, safe or secure failure conditions. We want to make sure that if our program fails, there's 4 traits that it has in the process of failing. And those are that the failure is early, and of course, object initialization is about as early as you can. Your program is just starting, is warming up. We want to fail safely, so there's no leaks or memory dumps or any kind of crashes that leave threads open or something like that. We want to have a safe failure. We want to fail explicitly, so the reason for the failure is known, so that upstream services can deal with the error, and so there's a way to catalog it and document it and maybe trigger an alert or response of some sort. So that has to be very specific. And finally, we want to have a singular point of failure. It is terrible to have to deal with a program that cascaded into a myriad of different failure causes when you have 5 potential problems that could go wrong. And you don't know. You just have like this giant log dump and you're trying to figure it out, right? So can we use those 4 conditions and apply them to the options pattern? Yes, we can, and we must. The main point here is that insecurely configured services should not even start. If something can be misconfigured, it will be misconfigured. It's just a matter of time. Our engineering should be up to the task. It needs to be advanced enough to anticipate problems and to quit naming the reason for the failure, naming the exact reason for the failure gracefully, so the whole thing spins down and we know what to do. How do we do this with the option pattern? Well, there's a small adjustment that we're going to make to the classic, and the adjustment is this. To our type, when we define our option, we will also add a return type error. So now it's not just a function that takes a pointer to the bank account, it also returns an error. So our validation logic will be now inside our option. It's not just a setter method, it's not just doing a modification, it's also going to do some checking, some validation to make sure that the parameter is correct. So once we have added this capability, now when we create our option with email, we will return the same closure, but this time it has the capability of checking for an errors, and we will validate the email inside the closure, for example, by using a regular expression, and return an error if it doesn't validate. In some languages, we can use, we can just throw an error. That's just a style question, right? So Go returns errors as values. I think that's better, but throwing is also an option. The point being is that this will translate into other languages nicely This is just an example. But what you are doing is checking, is this parameter absolutely legit in every possible way? Can it mess me up somehow? And once I know that it can't, now it's safe to ascribe or to assign to our main object, and finally we will return a null, meaning that nothing went wrong if the execution went all the way to the end of the function. That's a safer options type. How do we use those in a constructor? Well, that's what a typical constructor will look like. We'll call ours new bank account. It will take a list of options called, we'll name it with options, and return a pointer to our bank account and an error. So our resulting bank account will be just blank. We're not going to do anything with it to start with. And then what we will do is we will iterate one by one through every provided option, evaluate it, apply it to our result, and if there is an error, we'll return it. And of course, when we're returning the error, we also should be wrapping it, so it is clear upstream that this is initialization failure, that there was not something that went wrong in the execution stage, it went at the initialization stage. This helps with clarity and the stability of our service. Finally, at the end of the constructor, we want to validate the result itself, but not the parameters. So what this means, basically, we want to check if mandatory parameters were set, if it has all the right things it needs to have, and then we can return it and return nil for an error. Not too difficult, very basic example. There is some boilerplate, but trust me, it pays off doing this when it fits. How does it pay off? What does this really get us in the end? Well, rigorous or well-designed, documented application of the options pattern allows us to deal with three different things at the very least. And those are invalid and insecure state, right? We don't want to launch an object with something that's nil or something that's misconfigured and just broken, incapable of carrying out a critical task, which could have security ramifications. The second one is we want to prevent failures originating in parameters. Those are actually very common because as programs get more sophisticated, a lot of times a parameter being passed is a behavior, like a cache, for example. So you're passing that to your object, and that can have a lot of complexity, and you have to ask the question, how was that configured? Who configured it? Who provided values to that parameter? Do I know if it works? Usually we assume that just because the interface was satisfied or just because the thing was given to us inside the program, so we think, well, if it came from inside our program, it should be fine. Well, no, it should be validated, all right? There should be some basic checks because otherwise there will be failure originating in the parameter that can affect the rest of the program. So we want to guard against it, and the options pattern can help with that. And finally, conflicting parameters. A lot of times what will really mess you up is not one misconfigured thing. It's usually an interaction between parameters that can undermine or cancel out another. And those are also difficult to detect because the configuration itself can look rather benign, and something that's obscure and not as noticeable can critically impact something else, another part of your execution. The options pattern can help with this. I'm talking about how wonderful this thing is, and hopefully I can convince you, but there is definitely usage criteria. We should not be using this everywhere. Where should we use it? Typically, I use it, if I do use it, maybe once per package, once per program, not more often than that. Whatever you're configuring has to be sophisticated enough. And there's three criteria you can go by to choose if you want to really work with the options pattern. And the first criteria is flexible behavior. So does your object change the way it behaves based on environment, based on the configuration values provided? Are you passing providers or drivers or caches or networking layer adapters or any kind of adapter to your object? If you are, that's flexible behavior. And that means those parameters with behavior should be validated. So you'll need the options pattern. Second, if you have some mandatory parameters or but not others, or if you have a situation where the list of mandatory parameters can change circumstantially, right? So that's fairly sophisticated. And also, if they were all mandatory, you would be probably better off with something more straightforward, like a dictionary keyword initialization strategy, because that will be clearer, right? But if that's not so easy, right, that some are mandatory, others are not, the options pattern is probably a better bet. And finally, if you have entangled parameters. And what are those? It's a class of conflicting parameters where changing one produces a side effect that can cause problems or warnings or errors for another. Let me give you an example of what that would look like. Let's suppose we're writing a hypothetical asset encoder, and let's just put together an option for it. And it's let's say it's for an IoT device. It will be kind of something simple, not too sophisticated, but who knows. So we're writing it, and we're going to write an option called with block size and memory limit, and we're putting size and limit in the same option. And why? Well, here's the reason. Because size, block size, and memory limit have several conditions, several interactions with each other. They are intertwined. First, those are just three things I can think of from the top of my head, but if you thought about this problem or had to write an asset encoder, you can think of more, right? But first of all, the limit has to be greater than 0, and it has to be greater than size. The limit has to be a multiple of the size, because we don't want to end up with a block that's overflowing a buffer or underflowing a buffer in the end. Like that will just create a complex logic in the encoder itself. So to prevent that, we can just check, first of all, the limit has to be a multiple of the size. And third, we may have protocol constraints. Like we just, for example, know that in the protocol for this encoder, there's only 2 bytes for the block sequence, and that puts a limit on how many blocks total there can be. So those 3 things are significant issues and significant areas of interaction between those 2 parameters. So if you change size, limit will be affected, and if you change limit, size will be affected. In low-level languages like C, those simple things are deadly, potentially, right? Missing this can result into a remote code execution, a buffer overflow, a DOS attack, a crash. I mean, you can just imagine just about anything, right? So even with stronger languages like Go and Rust, even if memory is not corrupted, the interactions between parameters can still unbalance it and toss the service over. So what are we going to do about it? Well, we'll write an option in such a way that we validate all those areas of interaction. We try to forecast them, a threat model a little bit, and build that threat modeling into the code in such a way that when we finally assign block size and memory limit to our encoder, they were proven to be correct. They were proven to be safe. And then we return a null. You can see here right away that this also creates what we call self-documenting code. When the person is using your package, IDE will give them hints, right? So they start typing and they start selecting options. So they'll type something like, well, I want to change block size and memory limit. And they'll see by typing either one, as it comes up using the fuzzy search, that they go together. And the programmer may not understand the full extent of the relationship between those 2 variables, but just by consuming it this way through the IDE, they have a hint that they are connected. And this is documenting, this is hinting to another developer that those parameters are significantly connected. And this creates documentation that's implicit. It's very convenient and very helpful and more secure. Can we improve this even further? Yes, we can. We can improve the options pattern even more by adding option grouping. This can help us with isolation, clarity, and safety when we combine multiple options as one. And those options could be private or public. Let's look at how we would go about doing that. We will write a little helper, and we'll call it with options, that will take a list of options and return one option. Why would we ever want to do that? Because it's wonderful. I'll explain. So let's make that work, right? So let's make that option. We'll make a function that takes our bank account and returns an error, and we will iterate through every option and apply that option to our B, our main object, check for an error, and if there's no error, we can return. Well, this loop right there looks exactly like the loop we already wrote for the constructor. And we can just externalize it, right? We can pull that functionality out. So while we're at it, let's just replace the iteration inside the constructor by using our little helper with options, and not forget to include also the error wrapping to characterize the error as an initialization error. So this is a little bit of more boilerplate. Why? What's the point of doing that, combining multiple options into one? Well, this allows us to unleash our little helper and create option sets. And one of the best option sets you can have is called with default options. That's what it means to have a program secure by default, right? Is actually having secure defaults, and that means functionality that configures the object securely, but also singularly. How convenient is it to just find out what are the proper decent configuration values that I should be using with this class just by clicking on that list with default options, and then immediately I can see the entire list, the values that are expected, and it helps me decide what I might want to change, right? Or it helps me see what things are mandatory from a single location. That's excellent for clarity and security. With default options, it's great. Something else, you can also write an option set called with debug options. And those are wonderful. Why would we want to do that? Well, because we can write special unsafe private options. For example, like administrative backdoor that we don't want anybody just using frivolously. And we can hide that administrative backdoor option called with administrative backdoor. We can hide it inside an options set called with debug options. This way, it is entirely clear to the user of our API that this backdoor should not be used by itself. It should be used together with as a part of a set, and also allows us to attach instrumentation and all the other things we may need for debugging, trace logging, etc. together, because you'll never have a situation where administrative backdoor is deployed, but there's no logger attached to it, or anything like that. And while we're at it, while we're making those lists of debug options, why don't we also add a little check just to see if our service is running in production? Because if it is, we should be crashing it, right? We should not be deploying debug options into production. That makes it very insecure, and this way our little helper allows us to do it. And finally, we can also use our little helper for visual grouping and nesting. Sometimes three things are not really tangled, but it is helpful to see them on the same line and perhaps add a comment for clarity's sake. The little helper with options allows us to do this ergonomically and beautifully. Let's put all of this together so we can see the value. Let's look at some things that are more sophisticated than the simple examples that we were discussing. Suppose we're writing a hypothetical distributed secrets manager. Is that complicated enough? Oh yes, it is. This is hard to write. And since it's distributed, we will have peers, and we'll need a way to provide those peers to our constructor, maybe a peer discovery protocol, maybe both, why not? Also, we want to have a caching layer, because if it's distributed, it can be very impractical to wait for the round trip for the network layer, so we may want to have a cache. Redis is great, so let's just take a stack of Redis settings and wrap them in the adapter. We may want to do basic cryptography without revealing keys, and if we do, then we will need the option for providing ciphers to our secrets manager. So there's a way to control allowed ciphers. We want to also limit them to a certain list, and we can check for that list inside the option. And also, of course, the rotation window, right? What's the point of having a secrets manager if there is no rotation? It's absolutely critical. So we want to have a duration between which, at the end of which, we are expecting that the keys will rotate. And also we want to set max key lifetime. When you look at those two things, you realize that, wait a second, those two are pretzeled. Those two values have a significant relationship to each other. The rotation window cannot be shorter, cannot be longer than max key lifetime, right? Because if it is, we will have service outage because the key expired, but it wasn't rotated in. So it has to be shorter than max key lifetime. But also, max key lifetime cannot be too long. If it's more than like 5 times longer than the rotation window, then that defeats the entire purpose of the rotation, right? So it persists much longer and it increases the attack surface, and it creates other types of problems. But if we think harder about it, there's actually more potential problems. Because if we try to combine those two options, rotation window and max key lifetime, inside the same option like we did with size and limit in the previous example, it just will not work very well. First of all, that whole option declaration with rotation window and max key lifetime is very wordy. And then we realize that actually there could be more parameters that could affect us down the line. Maybe right now we can't think of any, but this could change as our secrets manager gets more sophisticated. But something else comes up. What if the cache invalidation was misconfigured? Our Redis cache, how is that configured? What if it's set up in such a way that the keys persist longer than their max key lifetime? We could have a situation where ghost keys are still in cache even though the secrets manager has already expired them. That would be a bypassed access control, and it's very easy to imagine a scenario where the misconfiguration causes it to persist for all eternity. So how can we address this? How can we do this securely? Well, we can lean on another initialization strategy, and instead of combining those into one option, we can just create another option. We'll call it Synchronization Strategy, and we'll take a list of keywords in a structure called Synchronization Settings, and we'll put the rotation window and key lifetime there, leave a comment, because we expect that maybe there'll be more synchronization settings later. We can deal with them later. But now we can pass that synchronization settings structure to our Redis cache adapter and synchronize the two so they are the same, that the max key lifetime matches the asset expiration, the value expiration inside the Redis cache. The options pattern helps us think and threat model. Maybe we could call it something like options-driven design. Maybe not. I'm just kidding. Let's keep going. New hypothetical microservice, right? So we're writing a microservice, and of course we'll want to provide a host and a port. We want to have a port as an integer, so we can lean on the type system. We'll need a TLS configurator of some sort. Acme is great, so we'll just use that. And then, of course, timeout settings. Timeouts are so critical for microservices. If the microservice is getting tar pitted or is getting connections which cause it to respond very slowly, or to or the other way, to hold long sessions, it can bring down the whole microservice. It can affect other microservices. So we can externalize that as well by making a structure called timeout settings and divide it into ingress, egress, and idle session timeout. And that timeout can be actually shared not just with the HTTP stack, but with other parts of the microservice. So the entire microservice is secured with all of its interactions, internal and external. You can use the same timeouts for interactions with the database. We may want to have an option for a secrets manager, because if we're running microservice, it needs to have secrets, KMS adapter to it, sure. A throttling strategy, right? If we're not throttling services, they are unstable. And of course, a retry strategy, we can call it immediate retry. We can swap it out for something else later. Those are behaviors, and if we're passing behaviors, we need to be checking them with the options pattern. And finally, we have a choice for a backend and a logger. If we are writing something so sophisticated that requires the options pattern, a logger is pretty much required. Yeah, right. We don't want to put loggers everywhere because they create side effects, but they're excellent for something this complicated, right? So, and then of course you can write an interface and satisfy it with a logger of your choice, and you can actually write the option in such a way that they are appended to a list. So we have now multi-directional logging. Suppose we're writing a Fargate containerized task launcher. I had to write one of those the other day. This is not easy. So Fargate is an API on top of Kubernetes, which is a nightmare to secure. So Fargate is a little bit easier in that regard. But still, we have to be vigilant, and we have to check the AWS config that it's correct, right? That it's not using static keys or anything like that. So we're using the configurator properly, that is getting its identity and its role from the EC2 instance where it's running on, not from an environmental variable. We can check for that. We want to provide a cluster name, so we have a single point of failure, a URL factory, sure. And then private subnet IDs and public subnet IDs. Well, see, Fargate does not differentiate subnets, public and private. It just has one place to put a subnet. It just asks for subnet IDs or a list of IDs. But that's a problem, because if we put a private service out on the public subnet, we could be leaking information or giving an attacker server-side request forgery type of vector, anything you can imagine. So we have to be really careful about that. And even if Fargate does not differentiate private and public subnets, we should. The same goes for security groups. Like in AWS, security group is like a firewall set of rules. It's very significant. So how can we differentiate? Well, we can, for example, when we get the subnet ID, we can check for that IP address and see if it starts with 10.0. That would indicate an intranet subnet. That's just an example. You can get more sophisticated than that. But the point being is that even if the API does not enforce public-private division, our implementation can, and our configuration checker can. We can check for that at initialization, and we should. Suppose we're writing hypothetical encrypted network tunnel. We want to specify a certain packet size, a key provider, yes, of course, a behavior, and we may want to have a recovery fallback if our network tunnel is stateful. A journal fallback is great, sure, let's provide that, and of course validate it as we're leaning on that behavior. We'll need a nonce factory. That's always a complicated thing with encryption. Synchronizing nonces against across services at scale is very hard. And finally, we can even use an option called with error handler. Those are great. And this is an example, another one, where we can pass a closure as an option, and that is so convenient because sometimes we don't even care about every error. Like sometimes we want to set up an alert, or we're looking for a report on a particular error, and we can do that with an options pattern using the error handler, append that to a list of handlers, and rock on, right? That's a really flexible, great way of dealing with errors, and of course we can have a default one in there as well. That would make our service more secure. Error handling is a big part of security. So those are just examples of some things I got to work on and some things you can think of yourself. But here's an elephant in the room that I did not even bring up. Something I didn't even talk about this whole time that's so important. Just think back. What are we doing with this, right? We're pulling that sophisticated logic, validation logic, into isolated closures, into functions that are localized, that each have to do with one area or two areas of concern and that are sensitive to each other but are very limited in scope. We are setting up our options for easy unit testing. Here's the truth. There is no better initialization strategy for unit testing than the options pattern. And once you have a strong battery of unit tests that check for many different types of failure conditions, you add security and you make it in such a way that it's modular and flexible and extendable, right? You're not going to break any APIs if you add additional options, etc. It just makes it great. Tested code, thoroughly tested code is safe, and the option pattern gives you a hand by lending itself to easy automated testing. OWASP Top 10 2021, number 5 and number 4. Security misconfiguration, insecure design. This is a problem that should not be in top 10, right? We can solve this. We have the tools for it. We have the know-how. It requires a little bit of discipline, a little bit of a different mindset. This is coming from functional paradigm. Functional programming paradigm is good. You can apply it, but most importantly, it can help you think and threat model and anticipate problems ahead of time. And if we use the options pattern, we can make a big chunk in this work that's required to resolve security misconfiguration and insecure design. Let's sum up. If something can be misused, it will be misused. Be secure by default. Weakened services should not even start. The options pattern guards against misconfiguration, invalid initialization states, and other vulnerabilities. The options pattern is convenient for automated testing. It is the best strategy, object initialization strategy for automated testing. And finally, implement the options pattern in your next major version release to bolster security with a boost of code readability, reliability, and resilience. This stuff really works. Use it. If you enjoyed this presentation, you can find a full compilable example at that QR code. I also want to bring to your attention a few resources. One of them is the classic presentation by Dave Cheney. This is one of the early discovery opportunities for me, how I learned the options pattern, and he explains even more all the great benefits of it. There's also a very detailed, good blog by Mark Sagi-Kazar that is excellent. And there's an interesting article about how this can be applied to database queries. Thank you so much for your attention. I enjoyed sharing the options pattern with you. I hope you learned something new and keep in touch. Bye-bye.